including AI and machine learning workloads, and have been in this space for a number of years now. Today, we'll be talking a little bit about how the mainframe and AI and okay, so I'm getting a little bit of echo. Okay, are we okay?
Yeah, I can hear you, Joe.
Yeah, I think we're good now. We can just mute.
All right.
Everyone else can mute. Yeah.
All right. So what I'd like to do today is okay. All right. So I'm sorry. I'm getting some delay in my headset, and I can't. It's
real quick. If you have the stream open, Joe, please close it from your Windows.
I have the stream.
Yeah, because there is no echo for us. So you sound pretty clear to me. So I guess it must be on your system somewhere. Yeah, perhaps you have the help in open as well. I'm sure.
Sorry. All right, that's better. I apologize, everybody. This is a user error. So I'll try to proceed here a little bit more quickly. My colleague and I, Alex, will be talking a little bit about machine learning and AI on the mainframe. And today, I'll sort of do the introductory part about the mainframe's place in the world today, and why, and perhaps establish a little bit of context as to why AI and machine learning workloads are important to this platform, and to the general public in general. For many of us have never seen a mainframe before, or never interacted with it personally. We've never laid hands on it, or even really seen a modern mainframe, and that can be a little bit difficult at times to just really appreciate just how important and integrated the mainframe is in today's world. So a lot of times, in the absence of being able to, say, hold one in your hand or use it like a tablet or a laptop or anything like that, most people get the impression, of the traditional mainframe, where you generally see things like a black and white photo like this. Is this clear on the feed? Yeah. Okay. Good. This is actually a picture from the 1950s, and this is at the U.S. Department of Agriculture, where one of the very earliest System 360 models were being rolled out. And so a lot of times when you hear about the mainframe in the news, you might even see this very picture rolled out as an example of what a mainframe is. If we move ahead to about the 1970s, you start to see something a little more modern. There's actually color in the photos, which is good. But still quite dated. These are 45 or 50-year-old photos still. If we move a little further ahead, perhaps into the late 70s or early 80s, you begin to see what is often referred to as sort of the room-sized mainframe that does really large volumes of transactions and a great deal of number crunching. And people like to talk about things like how much energy usage it had, and yet with all of the limited capabilities because of the technology that was available at the time, this kind of a deployment back in the 70s or the 80s, might be replaced with a PC today. And so this is oftentimes the visual that people have when they think of the mainframe. And if you look at this, I started my career with IBM not long after this particular kind of a mainframe configuration was sort of the state of the art. And just to explain this picture just a little bit for historical purposes, this box in the center is essentially the processing complex itself. You have disk arrays over against the wall, obviously tape drives against another wall, and all the boxes, all of the big orange, red boxes around the outside, do things like supply chilled water and electricity to the main central processing complex. So this is a very large system with a lot of environmentals involved, and all of it in support of the central processing complex, or CPC, in the middle. So this is what people are often presented with when the conversation of the mainframe comes up sort of in the general population. This is what a mainframe looks like today. This is an IBM Z machine. Z, I think one of our colleagues said in an earlier statement was correctly said that Z stands for zero downtime, and that really is true, because the mean time to failure for an engine on a mainframe is measured in decades, and not in months or years. A fully configured mainframe can have up to 190 CPUs, and these CPUs are really high performance engines that all run, roughly speaking, at about 5.5 gigahertz apiece. Right? So if you configure a full box, you might have perhaps 2 of these towers sitting next to each other to accommodate all the peripherals and everything. But the machine itself has 190 CPUs if you configure it fully, 40 terabytes of memory, and a really large I/O bandwidth. It's really important to note that a modern mainframe is often not used really to do computation as much, although it's very, very capable of doing so. The real strength of the platform is moving huge volumes of data into a compute environment, doing the computation, and then moving the results back out. And so for that reason, we have what are called I/O processors. They're essentially just CPUs that are dedicated to doing nothing but talking out over channels to disk arrays, to the network, and to any other I/O device that needs to talk to a CPU. And they're dedicated to that particular task, so that if you get a very heavy I/O stream coming in, it's not like on your laptop or maybe a home workstation where it can start to affect the performance of the system. You have dedicated processors that can speak just to those I/O devices so that you don't impact the performance of the machine. You can talk over 192 fiber channels simultaneously, and then the disk arrays themselves, the disk farms, are separate from the mainframe itself. You can take these and put them together through what are called coupling links to as many as 64 other mainframes to provide a virtual unified hardware platform. So think of this as if you fully configured an entire mainframe and coupled that with 63 other mainframes, you would have 190 times 64 different engines out there available to use, and up to 40 terabytes times 64 of memory capacity. The point is, these are configured to be enormous machines that can handle enormous workloads. Other things to highlight are that we have on-chip, not in a separate card, but actually on the CPU die, hardware devoted to compression acceleration, so that you can compress files in various forms down to very, very small footprint without affecting performance again. And the same thing with cryptography. Obviously, one of the main strengths of the mainframe platform is the security of the platform. And you may have heard of the term pervasive encryption, meaning that data on the platform is never in the clear. At no point, whether your data is on disk or in memory or in a channel or out on the network, at no point is that data ever not encrypted. And in order to handle that, you have to have hardware capabilities that will allow you to do that, again, without degrading performance and impacting your overall service agreements that people establish with the mainframe itself as it runs these different workloads. Similarly, along the same lines, along the zero downtime theme, a lot of redundancy is built into these frames themselves. So there are multiple spare CPUs that are incorporated in every box. So although we say we have 190 CPUs in the system, there's more than that there, and there are spares that are just waiting around to be brought online automatically in the event that you would take a failure. And in many cases, what happens is if a hardware problem is detected, the system will swap that CPU out, bring in a spare, and call IBM to say that there's service that's necessary, on a particular machine. And a lot of times our clients will actually get a call from IBM saying, when can we come and service your machine, because we know that there's a problem in your hardware, and the client will have never seen an outage or even a degradation in performance or throughput. And there are lots of other layers of redundancy meant to eliminate outages, from the way these things are configured to various redundancies built into a fault tolerance that's built into the operating systems and various middleware and applications that run on the platform. All of this designed to prevent taking an outage. Right? And so this has all been developed over decades. IBM is an expert at security and maintaining uptime in unexpected outages. So just some usage statistics: 92 out of 100 of the world's top banks use mainframes to process transactions. $7.7 trillion worth of credit card payments are processed annually. If you use an ATM, you almost certainly have talked to a mainframe on the back end with every transaction you perform. 29 billion of those transactions are processed annually. And if we're just talking about overall transactions across the banking sector or the insurance sector or any other government agency, for instance, if you count up all of those transactions and add them together, you're talking about 12.6 billion transactions every day. So the mainframe is there on the back end. It's a part of an invisible infrastructure that's part of our online world that we as end users don't see and use directly, but we use on a regular basis every day to do the things that we do online. You couldn't shop online without a mainframe. You couldn't bank online or even do a lot of government transactions as well without a mainframe on the back end recording the actual transaction. This is the world's system of record. So if you think about it like this, if you do any of these things, I already touched on some of these. If you file a tax return, or you use an ATM, or you make an airline reservation, IBM does a lot of work with the airlines as well. Reserve a hotel room or rent a car. All of these things will generate transactions that eventually are satisfied and recorded permanently as the system of record for any of these online activities that you may pursue. And there are literally exabytes of data out there that are managed by the mainframe, and these are all what are considered to be dark collections of data, in the sense that they're private, they're sensitive, they're confidential. And if you go out and try to search for these kinds of things, you're never going to find them, because they're kept proprietary and behind privacy walls for very good reason. And so it's easy to overlook the essential role of the mainframe, because all of these things are behind interfaces that are designed to prevent publicity of what the contents of that data are. And so while you oftentimes will hear various stories about how such and such an external tech company may process large volumes of data, the fact is that most of the world's data resides in these back-end systems. It is confidential and private, and not subject to people even knowing necessarily how much data there is out there. The point is, the mainframe platform manages enormous amounts of data, and we take it for granted. We know that it's there, but we don't physically touch it or interact directly with it on a regular basis. So it's really easy to overlook the essential role of this platform in our everyday online life. So with that as a context, with that as a context, I'm getting some comments in the chat that that we're getting some glitches in the presentation itself. I hope this looks better. All right, let's continue on. Okay, good. So along those lines, knowing the mainframe's role in our online environment today, how does AI and machine learning fit in with this particular platform, and why would you even worry about or think about AI as a workload that ought to run in this context? As it turns out, when it comes to the world of transaction processing, there's some very important roles that AI has to play, particularly if you're looking at things like how to prevent transaction fraud in real time. That is a key workload that needs to be run on the mainframe, so that instead of a bank or a credit card company just accepting a certain percentage of losses every year to fraudulent transactions, if they can build AI into their systems and exercise those AI workloads in a timely fashion in line with the transaction, they can prevent fraud rather than accept the loss and make that part of their cost of doing business. So in order to service those kinds of transaction-based AI workloads, we embrace sort of 3 industry-wide themes that are part of the enterprise AI environment. The first is data gravity, and that's many of us may know this already, that it's the approach and philosophy that transactions should be brought near to the data. And the further that you separate an application or a transaction from the data that it acts upon, the less efficient you're going to become, the more expensive it's going to be to operate. So you're always better off if you can move your computation to the location of your data or get it as close as possible. And we've worked with customers all the time who have data on their mainframe. They've generated a transaction stream, and for whatever reason, their particular applications are strung across the enterprise. We help them to repatriate those applications on the same platform or near their data, and suddenly things become much more efficient. So this is especially important when your data set is really huge, and by huge we mean petabytes of data. The other theme that is part of this AI and ML environment is the idea of data latency. Once a transaction is recorded, it exists forever, right? It'll get logged, it'll get recorded and used for future reference. But the sensitivity of that data and the value to the bank or to the credit card company or to the online retailer, the value of that data degrades very, very quickly. So in other words, if somebody goes and makes a purchase and you want to act upon that data as a retailer, for example, you want to do that as quickly as possible. It's not okay to go back and look at historical trends in data and perhaps follow up with an offer to a valued client a day or a week later after a purchase is made, because most of the time acting in the, either within the transaction or very close to that transaction will yield a much better result. And finally, data security, which we've touched upon before, is also very key to this environment. There are always, we all understand the news stories out there about data breaches and how damaging that is, not only to the reputation of the company where the breach occurs, but to all of the customers and clients who have their personal information exposed. One thing to keep in mind is we often talk about data movement, but there really is no such thing. There's data copying. If data moves from a mainframe to another machine, we don't erase it from the mainframe. You've now created a copy. Once you have 2 copies in place of 1, now you have a data governance problem where you have to think about, okay, I've now created the second copy. If I update the first, if a new transaction comes in or there's an update to the system of record on the mainframe, now my data that's off platform is out of sync. And there's all sorts of problems that go on with that. So if you can move your application to your original data source, you will reduce or eliminate that kind of data governance problem. So I'm going to close here. I just want to follow up with a little story that a friend of mine told me years ago. she said that one time she was out visiting a client across the border from the States in Canada, and had completed her particular business trip and was on her way home. And as she got up to the border, she got stuck in an enormous traffic jam. And just about the time she was sitting in traffic and trying to figure out what was going on, she got a call on her phone that that they were having a high severity problem that was called in by Border Patrol and U.S. Customs. And so what she had done was help everybody go through the debugging process and try to come to a resolution, or at least a workaround that would help this particular client out. And as she got done working through that problem on the phone, it occurred to her that was the reason she was sitting in traffic, that the very problem that she worked through on the phone was the reason why she was blocked at the border and she couldn't get home. And so it just really drives home to you, to her in particular, that if the mainframe permeates everything that we do online, and it just is such a central part to our modern lives these days. And whereas maybe with other platforms, an outage might cause an inconvenience, this is a different kind of inconvenience. And it's important to continue to recognize and remember that the mainframe is the background of all of these systems, and it's completely vital to everything that we do online. So just with that as some context, I'll wrap up. I know I'm a little bit over already. And I'll hand over to Alex, who can get into the real data science part of this, and wish everybody well as you go on through the hackathon. We're really excited to have everybody look at this platform and this set of workloads as a viable activity on the platform. So thank you for your time, and look forward to working with you.
Yeah, thank you, Joe. Yeah, and I'll start sharing and take it from here. I hope everyone can see my screen now. All right, yeah, I think you do. All right, so yeah, my name's Alex Asaichi, and I'm Solutions Architect here at IBM. And specifically, I'm focusing on IBM Z platform, working with partners, different software vendors, independent software vendors, and help them to create, build their products on our enterprise-grade IBM Z platform. And this covers all ranges of solutions in hybrid cloud, machine learning, AI, and we have also Red Hat, IBM software that can span across public clouds, private clouds, and also IBM Z infrastructures. And of course, machine learning analytics is also a big part of it. So as Joe mentioned, right, IBM Z is an enterprise-grade hardware with different hardware accelerators that is designed to run millions and billions of transactions and host thousands of users. So today I'll demonstrate some typical use cases of analytics and machine learning on Z, and also will provide you with access to the environment. So you'll be able to experience firsthand IBM Z, and specifically analytics and machine learning in IBM Z, using your familiar tools, but also in the back, those models that you create will run on IBM Z and actually ZOS part of it. And that hopefully will give you also a better feeling of like when to use it and why to use IBM Z for this. Yeah, and yeah, if you look at the architecture part of it, there are two. It consists of two parts, right? So if you, from the user perspective, you will interact with a web UI, web interface. So it's all user friendly and visual. Then the interaction, the front end part, is actually running on the Linux side of IBM Z, and the actual machine learning and models will be running on the ZOS part. And IBM Z in this regard is extremely valuable tool for data scientists because it can streamline the process of translating your prototype models that you create, let's say, on your familiar tools, maybe cloud, maybe Linux world, maybe on your laptop, translate those into production grade model workflows that can run on the ZOS in the back, and be able to serve tens, hundreds, thousands of users at the same time. And if you look at the typical end-to-end process as a data scientist, right? So you start with experimentation phase, right? So you have an idea, you have some data, you have your laptop, maybe some online cloud tools. So you look at the data and your goals, objectives. You maybe run some statistics. You visualize the data. You create a model. Then to create a model, you of course need to try maybe hundreds of different machine learning algorithms and see which one would give you the best prediction results, best accuracy, and so on. And this is the fun part, right? The experimentation is done. Maybe you created your model, an algorithm, right? And then when it gets to building this model, that's when it gets complicated. So you need to compile this model. You need to optimize it, make sure that it runs quickly, that accuracy is high, right? That's already, it gets harder at this stage of the journey. Then after this, you have to train the model, right? And then in this stage, it gets again a little harder because you need to train it on more data. You need to start dealing with large amounts of data in order to get better accuracy, in order to train it on more cases and variations. And then finally, it comes to serving, right? And the serving part, you basically have your model trained. You can do predictions, and you show it maybe to your friends and your boss, right? And everybody likes it, and they say, yeah, great job. You done great machine learning model there. And now the boss says, okay, how can we put it in action? How can we put it in production? Can it serve 10 users? Can it serve 100 users? Can it serve 1,000 users? Right? And then if your model, let's say, runs prediction and it takes like 30 seconds even, right, to do the prediction for a single user, then how can you do it for 10 or 1,000 in a reasonable time? And then that's when you need to start looking into, okay, you need to make your model converted from a serial to parallel, right? So it executes in parallel, does some maybe transformations in parallel, and then merges the results. Then you probably want to run multiple copies of that model. And then the requirement comes, okay, now we have streams of data from our customers, like, maybe transactions, credit card transactions, or any kind of events that is happening in real time, and we want your model to be able to process these live transactions, maybe train it, periodically retrain your model, and then show real-time predictions so that we can immediately maybe detect if there is a fraud, or maybe provide some valuable insights into the events, so those 1,000 events that are going on. And that's where IBM Z comes real handy. The system that can run thousands, millions of workloads. For example, on a single Z machine, you can run 2 million Docker containers just on a single server. And that's where IBM Z becomes really handy, where you can run your models at scale, and also where you have all the data, all your billions of transactions stored, which Joe mentioned, the data gravity concept, where you want to run your analytics as close to the data as possible, so that you can really ensure those the fast responses and the best efficiency, so you don't need to move the data and lose time on moving this data and analyzing it somewhere else. Then the ZOS part here, and ZOS is the operating system for IBM Z's. So it's a 64-bit system, and it has at its heart a workload manager, which is, you can think of a kind of a hypervisor or maybe container runtime that can manage those numerous concurrently hosted units of work kind of happening at the same time, and which also can run in separate and key protected address spaces, right? So you don't want to mix up with like different users in the same time. So you have those tenants running in separate address spaces. And then at its heart, unlike maybe like Linux systems have file systems, files and folders, right? ZOS has actually data sets and catalogs, right? So you can think of it as maybe a database instead of the file system there. Then you have a Linux side, which is on the same machine. You have both maybe partitions, and one runs ZOS workloads, another one runs traditional, pop kind of typical Linux workloads, right? It could be Ubuntu, it could be Red Hat, Linux, all the well-known Linux distros can run. And then you have your front end and popular tools running on the Linux part, and that's what we have in our environment here. So we have Jupyter notebooks running here. There are some Docker containers. There is a MongoDB database. So popular tools from open source world can run on the Linux side of it. And then you have IBM Open Data Analytics for ZOS, which is also built on some open source blocks here. And this runs, which is also called IZOTA, right? This runs on the ZOS side here. Okay, and from here on, let me switch to the actual demo. So the environment will provide you access to, once you register and sign up, you will get to the dashboard where you can see the you can see the instance which you were assigned to, right? As you can see here, analytics instance, right? And that's the ZOS instance running in the back. And you're given a username, and in this case, username also represents the instance name. What you will need to do is change the password here, and there are restrictions I'll show about what password should be. But you can use, which is simplest, you can use maybe the same password as a username, right? Because you will have to enter the same password later in your Jupyter notebooks. You will start your instance, and once the instance is started, you will see, okay, ZOS status is okay, means your ZOS instance is up and running and is healthy. You'll click on the Jupyter, and this will take you to your Jupyter notebooks, where I already uploaded some of the notebooks from the samples, and I will share the link in GitHub later. And you will be able to run those samples, and I did run them already, right? And if you're familiar with Jupyter notebooks, you will not really see any big difference from running these notebooks on the mainframe on IBM Z versus running it somewhere else. So the first demo, the first example here is using Python 3 and some of the sklearn libraries to do predictions for business in terms of loss of the revenue. And you can think of it as, let's say, if you work for a credit card department in a bank somewhere, right, as a data scientist, and you are given your tasked with to determine for your customers to predict based on the customer churn rate and maybe some other characteristics, other features, whether this or that specific card holder or card is going to be profitable or not, right? So that you can do some processing real time for all the data on how the cards are used and activity, and be able then to maybe provide the predictions and maybe raise some alerts or flags and say, hey, maybe this card should be canceled because it's not profitable, or maybe there's some other card should be motivated or stimulated to be used more often, and so on. So in this example, what you will do, you'll see like they're structured in a way that there is a comment here, and then there is actual Python code. So you will provide the username that is yours from the dashboard, and then the password. See, I kept those two the same. And then what it does, like the first step here in Python, right, it imports the pandas library, pandas for doing some manipulations of those data in data frames, and also numpy arrays, right, for the data, hosting the data. Then the next step, it will set up a ZOS data connection, right? So data is stored, and the data can be loaded also to your instance using the dashboard. So let me quickly get back to the dashboard here. So you will upload your data. That's what I did already ahead of time, but you will upload your data here using the dashboard. and you can upload either DB2 data in the special format or maybe a CSV, right, which is a more common format you will find online. So you upload the data, and then you can refer this data, you can reference this data from your Jupyter notebook, from your Python code. So basically what we will be doing, we'll be loading transactions, credit card transactions, and we also will be loading customer information into Pandas data frames. And here, for example, we load the data from DB2. DB2 keeps the transaction data, credit card transaction data, and we can output it here also, so you can visually see what is that data, what is that, how is the data formatted, right? And there's some timestamp, date timestamp, there are proper transaction IDs, the bank information, and also the more important for us part is, yeah, the transaction amount, right? So means there is for each transaction, of course, there is a card associated with it, which is also linked to a customer. So you can see, like, for each customer, how many credit card transactions they have per day, what is the amount, and so on. Then we load the client data or customer data, and customer data includes some information on the customer, demographic information, but also information about the annual income and activity level. And then the churn rate, so something that we are interested in predicting to understand if the card will churn and whether it will churn for loss or a profit, right? Okay. All right. And first step, or the second step after we loaded the data, right, we'll do the we want to do some aggregate statistics. Yeah, for example, you want to probably calculate the transaction amounts, aggregate the transaction amounts to find out what's the average transaction amounts per customer, daily transaction amount per customer. Then if there is any data missing on a particular day, so you want to normalize the data, you want to zero out those days, right, so that your data is accurate. And then you can again output it to see what are the averages that you aggregated there. Then after you're done with aggregate statistic, you start doing your exploratory analysis. And in this case, in addition to the analytics tools, libraries, you start using Matplot library to do some visuals, so you can visualize the data. And at first, what you want to do is you want to plot maybe data on and build the histogram on the annual income versus age, right? And just get some visual idea. Okay, how is the income correlated to the age, and how the dots in the scatter plot are placed here. Then you start making actually correlations, because you have a number of features for each customer, but you want to see which feature correlates the most with the churn rate, right? So we have the churn rate here, and then we have other features, you know, gender, age, annual investment rate, and also amount, and then income and activity level, transaction amounts as well. And you look into correlations, right, which is red shows the highest correlation, then zero, no correlation, and then dark blue is a negative correlation. In our case, we are looking for blue, dark blue colors, because we want to find which features correlate in a negative way the most. And that's where churn correlates negatively, because we want actually to find out the loyalty part, right, which is opposite to churn. And we see that, hey, churn correlates negatively with age and activity level, right? These two are the most interesting features we want to do the analytics and predictions. So yeah, now we did that plot, and now we want to focus more in depth and explore the churn rate in in the context of those two properties we identified, which is age and activity level, right? And yeah, we build the two histograms here. Green represent the churn, blue represent the no churn. And then the histogram has churn rate versus age years, right? And we can see here that, yeah, green shows that, yeah, there is a higher churn on the younger, in the younger people, and then there is a lower churn and higher no churn in the mid-age and kind of older people. So now we want to also add activity level to the mix. Excuse me. Yeah, and we want to see churn based not only on the age, but also activity level, right? And yeah, for that, we are using the, the graph, which is, which is called the box plot. I think, yeah, that's a box plot chart. Kind of shows same colors, use same colors here. Did churn, did not churn. And we want to see activity level and age and how the churn kind of maps to it, right? And you can see here that the green green is mostly present, heavily present in the younger age and lower activity levels. And then blue is mostly present at the higher activity levels and also older people here. Yeah, we can also do the bee swarm plot, which will show us similar picture in the dots, again, age and activity levels. And then we can now move on to, we kind of confirm that, hey, age and activity will definitely give us a prediction of the churn. So now let's create the model. And here we just chose random forest classifier, but yeah, we can definitely try and mock all various different classifiers as well, just see which one better works. But yeah, in this case, we chose a random forest classifier and we want to train our model. So we basically create the predict and train functions, and then initialize the model, train it, and do the predictions. Then based on predictions, we also want to calculate not only the churn, but we also want to see and be able to predict the loss. Remember, this is a bank, right? So we want to do, we want to tie it to the money and revenues here. So yeah, we calculate the revenue from each client and then multiply it by the churn probability, right? That way we'll determine our predicted loss per credit card per client. So we got our worst calculation, right, for each credit card, and then we also got our churn probability. Yeah, we show the table, but then we go and build the model which would predict, give us predictions for the loss based on the age in this case. And yeah, as you can see, the lowest loss is in the mid ages here, and the highest is in the younger ages and older ages here. And that's the model we built. This is an example of using Python, right, and Anaconda on in Jupyter notebooks and running it on the ZOS side. The next example is PySpark, right? So as you probably know, Spark is the tool to do general purpose computing that also can be scaled, right? So if you need to scale, like what I mentioned earlier, you need to scale your model to run in multiple copies, right? And also scale it over multiple workers. You need a framework around it, right? And Spark is a popular framework, and Spark is built on top of concepts, big data concepts, and frameworks probably known. You may know from before, which is Hadoop and MapReduce. And it uses an in-memory engine. It's an in-memory engine, and it does analytics in memory using the resilient distributed data sets, which is RDDs. So in this case, we do a similar. We have the similar data, which is the customer data and also the transactional data. But instead of using Python, now we're going to be using Spark to do the computations on the Spark instance. And just to quickly show you as well here, like on the architecture. Yeah, we have Spark engine here, right, as you can see. And Spark has different workers, so it means the instance which you will get, you will actually get one Spark worker, and you will be able to access the UI and see the Spark and see how the jobs are running there. And it gives you kind of perspective where, the Spark, there is a Spark master and there are workers which will be running your job. So you will be submitting your training and prediction job to the Spark, and Spark will distribute your job and kind of place it, dispatch it, and place it on the worker, and then worker will do the work, run the work, and then Spark will collect the results and kind of present it back to you in the Jupyter notebooks. So for the Spark, we'll be connecting to the Spark cluster using same ZOS username and password, but in this case, we also need to provide IP address. And make sure that you use the same IP address from the dashboard here. This IP address here, which is given. And yeah, you will be able to connect to Spark in this case, and then load the data. You can output the data as well. And it's the same data with transactions and customers. So then the only difference this time, we're going to do prediction using logistic regression, and also we will use activity as the feature instead of the age, right? So we use the logistic regression here, and we're using the PySpark machine learning libraries in this case, and we'll do the prediction based on activity, right? And yeah, once the predictions are done, so you basically use again, you train you have the train data set, you do the fitting of the model, transform it, and then you do the prediction, output the results, and then visualize the results again, right? So in this case, it shows us the probability of a churn based on activity level, right? And the churn probability drops drastically with the increased activity level, right? So that kind of allows you now to run this model probably on the actual active transactions, and then be able to do the predictions as needed. All right, so I'm getting some messages here. Okay, all right, that concludes the demo part. Let me quickly show you the information, and I'll post this information also in the in the channel there, so that you will be able to get back to it and get the access to the environment.
Awesome. Thank you so much for that, Alex. That was a really insightful demo, and learned a lot. That was very, very insightful. So go ahead.
All right. I'll post the data, the access information, how to access the environment in the channel, so that everyone will be able to access it. Yeah.
Awesome. All right, that sounds really good. So and then we'll also please, anyone who has any questions, we will be fielding them at the end. So please post them if you'd like, and we'll answer them at the end. And so with no further ado, we now pass it over to Kaivi and Daniel to share about their experience with IBM Z and machine learning, and how they were able to actually make a solution using these technologies, and a little bit about how you can also succeed with this technology. So thank you so much, Alex, and now on to you, Daniel and Kaivi.
All right, thank you.
Okay, I guess I'll go first. Hello, everybody. My name is Daniel, and I was a in SacHacks in 2020, working on a project that we called Viral Watch. And in that project, we analyzed the growth of some obscure virus called COVID-19 that nobody really cared about back then. And we used machine learning to predict like future outbreaks, as well as like optimal travel routes and the like. And we used IBM Z because of like the really convenient scaling of our models production. Because in like previous hackathons, I was working on like teams where we'd have to like wait around for like hours and hours to like wait for your model to train, and it's really just inefficient and frustrating. So one thing that I really liked about IBM Z was that we were able to use any tools that we liked. For us, we trained our model using TensorFlow. It gives you a lot of freedom. It's basically a machine that you run it on, so you can run anything on it. And I definitely recommend it because it seems really intimidating at first, just like to learn something new, but it's actually a really easy learning curve. Just picking it up and running whatever you'd usually run on your computer on it. And that's all I have.
Hello, everyone. I'm Kaivi. I'm here on behalf of my team, sharing about what we did in the hackathon last year. And I'm going to share my screen. So hopefully everyone can see this. Okay. So Unveil the Burn is what we created, and it is a deep learning platform that is used to assist and inform burn victims 24/7. It could detect and diagnose burns of varying severity, first, second, and third degree burns. And our motivation behind this project was to be able to prevent the general public from getting any skin infection or diseases that are caused by mistreating skin burns. So we wanted to create something that was easily accessible to healthcare workers as well as firefighters and patients. So it would allow users to, right here, upload an image of their burn, and we would analyze the severity using our machine learning model and return a diagnosis with the appropriate treatment recommendations. So we trained a neural network on data sets of burn injuries using scikit-learn on a Jupyter notebook executing on the IBM Z mainframe. And once this model was trained, which was extremely quick, using the IBM Z mainframe, the model could assess the kind of burn the patient has based on color, blistering, and breath. We were also a huge benefit of using IBM Z was that we were able to train our model on the mainframe and receive the accuracy results extremely quickly. Even though our test data set contained several images that needed to be individually parsed. The IBM Z mainframe sandbox environment did have a memory limit, so since we were using pictures of burn images of skin burns to pass through our machine learning model, we actually needed to resize these images in order to pass it through to the model on IBM Z mainframe sandbox environment. But this actually turned out to be very beneficial as it increased the model's accuracy that we were creating, that we were training on, because we used a lot of image processing techniques like content-aware resizing and foreground extraction. So all in all, my team and I are extremely thankful for IBM for allowing us to use the IBM Z mainframe for us to easily and efficiently run, train, and test our convolutional neural net, and later to train our more accurate, fully connected neural network for the analysis of skin burns. And yep, thank you.
Awesome. Thank you so much for that, Kaivi and Daniel. So now we'll just open the floor for questions. And if anyone has any questions that they'd like to share, please let us know and we will start fielding them. If not, that was mainly it for this workshop and presentation. I thank you once again, everyone. And please feel free to let us know what else you're looking into. Okay, awesome. So I guess there's no other questions for now. As always, if you do get some more questions down the line, please post them in the Discord channels. And the IBM has their own Discord channel for this, and so they'd love to help take any of your questions you have. So thank you once again, and big round of applause to all of our presenters today for this workshop.